So here we go. Good morning, everyone. So we are on lecture module one, chapter one. I'm going to be covering chapter one today. Just some quick notes here. I did update CISS100.com. If you recall, I stated I do record everything. So yesterday's presentation, the day one kind of course introduction, is up now. And again, by tonight, I'll probably get today's recording up. So in lecture module one, recall that we use two sites. There's CISS100.com, which has information. I use it for the presentation, allows me to really present, concurrent or current and relevant information. So I did cover navigation. And then, of course, Blackboard, where all submissions take place. I want to cover something real quick here. I asked everyone to read, of course, lecture module one, the emergent disruptive change. But I want to, again, just to make sure that we're all keeping this in mind. Of course, there's Moore's Law, Gilder's Law, etc. But the business IT society, or also known as the business organization IT triangle. One of the things we do when we assess anything in this discipline, well, first we are concerned with security. Whenever we have a new technology, how secure is it? But also, we recognize this business IT society triangle. And this is not in the textbook, so we'll not ask questions on this in quiz one. We recognize this triangle because it's integrated. Everything we do has effects on the other. So as an example, when some new technology comes out, we're developing the technology for one purpose, but rarely do we see all of its applications or ramifications, all the ways it can be subverted and used kind of improperly. So we'll have some new technology will come out and it will drive changes in society, may drive changes in business. Or maybe a business decides it wants to change its business practice. So it needs some new type of technology. Or society, maybe some legal issues, financial accounting, okay, now requires organizations to retain their emails for 10 years. That's going to drive changes in both business and IT. So again, we have this IT, business, society triangle. And whenever there's a change in any one of these vertices in the triangle, it's going to drive changes in the other two. And we need to recognize that. Again, whenever a technology is introduced, rarely do we see all of its positive applications and all of its negative applications. So I'm going to jump into chapter one here from the textbook. And again, there is a quiz associated with this quiz one. Recall the numbering is consistent, right? Lecture module one, quiz one, Linux lab one, okay, discussion board one. That one being, of course, it's all associated with lecture module one. So whenever we study a new discipline, quite often that first chapter is an overview. And we see this successively in computer science. We learn at the top level. We don't throw students in at that bottom, architectural level right off the bat. We teach from the general and then slowly get more and more specific. This actually defines or is defined by abstraction. In many ways, computer science is the study of abstraction, okay? The process of removing physical, spatial, or temporal details or attributes from the study of objects. And we're going to see this, right? Because I use the example, I can't put a car into the computer to perform a traffic simulation. What do I need to do? I need to represent it. I need to represent it symbolically. In other words, it's abstraction. And we deal with this every day in our everyday life, a car. When we get into a car and drive it, we interface, of course, with the steering wheel, the brake, the gas pedal. I don't think about the actual timing of the car, all the interrelated parts that go into it. I'm concerned with driving it, that high level abstract interface. And we deal with this in our computing, right? Everybody's looking at a screen, a real nice graphical user interface, GUI. You're not thinking about the actual execution cycles of your computer, what's taking place in memory, right? The communications that's taking places. We don't concern ourselves with this. So in many ways, computing is the study or represents abstraction. Okay, so as we study computing, especially in this textbook, we are going to continually get more and more detailed, more and more specific. Okay, so I gave this example. Now, I just used the example of a traffic simulation in the computer, representing that, symbolically representing it. So we abstract the model and represent its properties. But what are the two general classifications of an object's properties? And again, this is not in the textbook. So I'm just giving you things to hopefully think about. When I look at a car, what are its properties? Well, there are two general classifications. We have its physical attributes, right? It has four wheels, has some kind of structure, steering wheel, all these things. But then it also has behaviors, okay? It can drive down the road. It's very straightforward to represent an object's attributes, right? Four wheels, steering wheel, gas pedal, brake. But I also have to model what it can do, its behaviors, right? And those are processes, or more appropriate, programming. Okay, so keep this in mind as we move forward and represent our world. So moving now to the textbook, kind of the first page. What is a computer? What does it do? Okay, computer is a programmable. This is the key component here, because of course we can run many different programs. The computer has high utility because it is so flexibly adaptive. Electronic device, yes, okay. I'm going to introduce that this is actually present day modern computers ascribed to the von Neumann architecture. But I'll delay this until our chapter on hardware when we actually look at this, the von Neumann architecture. Accepts data, performs operations, and stores the data. So what we define here is the input, processing, output, storage cycle. Now, just so you know, most textbooks only treat this as the IPO cycle, input, processing, output, because storage is not inherent in every operation. And I can give an example of this. If I were to open up a new page here in my browser, right? And up in my location bar, I did this last class, so you see it 2 + 4, right? And it brings me back, gives me the answer 6. That was never stored. That was never written out to my hard drive, okay? So I guess what I wanted you to take away from this is every textbook will have little variances. So don't treat this as gospel, right? The computer cycle is input, processing, output, and storage. Well, no, this textbook says storage, but storage, writing out to my hard drive, that's the storage device, is not in every input, processing, output component. We also have communications, sending and retrieving or receiving data. And think about this. What did I say? Well, with everything we do moving forward, we're going to think about two things. Computer security, whatever I do, first thing I do, what are the security ramifications? But I'm also going to look at the IT business society triangle. And that doesn't really apply here, but with communications, that has a direct effect on security. Consider, if you will, you have a computer. What if you never connect it to a network? How secure is your computer? Pretty secure. Probably don't need antivirus software. Okay. So just kind of hopefully to drive that home. So the basic operations of the computer, input, processing, output, and storage. Note that this scales, okay, from the device up to the information system, which means we see it over and over. In our chapter on hardware, we're actually going to look at the execution cycle, what actually happens or occurs at the CPU, central processing unit level. Well, the CPU gets input from, I'll say memory at this point. It can come from the cache and registers, but I'll say memory. It does processing, and then of course provides or results in output, which by the way goes back to the cache or memory and does not go out to storage. If I look at my computer here, right? We're all looking at a computer. As I scroll here, that's input, my mouse. Processing, well, it updates the screen, and output, of course, comes out to my monitor. Again, no storage. But this also occurs at the information system level, the big aggregate level. If you think about your registration for classes at the college, what'd you do? You input your desired schedule, right? Input. A lot of processing took place. You were put in that class, your financial aid was calculated, your schedule was output, all of these things. So we see this input processing output model repeated from the very small CPU out to your system, your computer, even to a full-blown information system that probably has many components within that mainframe and system architecture. Okay, so to begin, we need to model the world. We need to symbolically represent whatever it is we want to look at. So we need to understand the information hierarchy. At the lowest level of the information hierarchy is data, raw, unorganized facts. And this can be, take place of or form of text, graphics, audio, video, many different things. Information is data that has been processed into a meaningful form. In many ways, you can think of this as it's now been given context. And of course, information processing is this process converting data into information. Again, this is kind of esoteric. Let me show you an example. It really shows it real quickly. Data, 012569856, data. Does it mean anything to anyone? Well, it really shouldn't. Some students actually have guessed what this is, and that's fine. But really, this could be anything, as their guess, of course, could have been incorrect. But if I give it context, if I put it into a table, and in that table, I give it the heading SSN, immediately everybody knows what I'm talking about, right? And note this, there's a lot more that took place. You saw SSN and immediately thought, oh, social security number. Your brain did that translation, right? Without even knowing it. It was just understood, right? So I can see that just putting it into a table, information processing, gave it context. But there's more that we know about social security numbers. We know it's unique text, not a number. Come back to this in just a minute. Corresponds one-to-one with an individual. This is now raising it up that information hierarchy now to knowledge. And why is that important? Okay, translation. Because really, when we communicate with other people, interact with other people, we're dealing with it, at the knowledge level. Think about this. Other countries probably have something similar or equivalent to our social security number. Some unique, string of characters, again, I'm saying characters, not numbers, that identify an individual with a one-to-one correspondence. And if this is the case, if we can encode this relationship, that it's unique text, that it corresponds one-to-one with an individual, in some other country, France is the same thing, then we can actually convert between the two. That's very important, actually. Now, returning to this, I said it's unique text and not a number. Can anyone think why? Why would I represent these as characters and not a number? Again, we're representing things in a computer. Well, if a computer determines or evaluates this as a number, what happens to that leading zero? It's gone, right? What number is 008? It's 8, right? Leading zeros are insignificant. They're thrown away. But in this case, in a social security number, that 0 is significant. So we have to be concerned with this, modeling our world, but also how does the computer represent it? Okay, so again, this is that exacting attention to detail that is required. And again, I understand that nobody has been forced to do this to this date. That's what we need to learn to do. So, and it is a learning curve. I understand that. I went through it. We all go through this learning curve. So don't be discouraged. We will make mistakes and we will learn from them and we will get better. Okay, so here's that information hierarchy I alluded to. Data, and again, with information processing, we move it up to that information level. knowledge, and at the very top, wisdom. And I present this picture here with this, this is representing a red light for a purpose here. So the data, the light is red. The information, well, where is this red light? It's a stoplight sitting at some corner, okay? Context, well, I'm driving towards it. And wisdom, I better stop the car. And I present this because this top level, this wisdom here, is the level of artificial intelligence. This is AI. To get to this level, we need to process and encode, represent the data, the information, and the knowledge. And I'm going to introduce something else in information systems, and this is critical in AI. Information must be complete, accurate, timely, and relevant. And I'll present this again when we get to systems analysis. But this is very important especially as applied to artificial intelligence. Because if that data isn't complete, who knows what the output, what the result will be. Okay, so I'll defer that. And I'll speak increasingly of this throughout this course. Okay, when we study any discipline, we study the discipline also from a historical perspective. Puts everything in context, information processing. So we study computing and we define generations, okay? And the textbook does that for this. So we're going to look at hardware based on the 4 generations of advances in computing. The textbook will also present programming languages from a generational perspective. First generation programming language, second generation programming language, etc. A lot of texts will also present operating systems from a generational perspective. This textbook does not. But we should recognize when we look at the first evolution from the first generation to the second generation of hardware, we did see the evolution of programming languages from the first generation to the second generation, and we did see the evolution of operating systems from the first generation to the second generation. So these all occurred rather in lockstep. The progression from the first generation to the second generation of hardware to software and operating systems. And I will present it this way as well. Now, I'm going to present it just kind of superficially here, and I will come back and do it in much greater detail, abstraction, when I get to the chapters on operating systems and programming languages. So prior to computing, we look at pre-computers, early computers. And the notable suspects are here, the abacus, the slide rule, etc. But I want to alert everyone to something I hope everyone will do, is continually evaluate. Just because a textbook says it's the abacus, slide rule, and mechanical calculator, it's not constrained or confined to that. Early in my teaching, I had a student, mention, well, what about a weaving loom, right? Early, textile manufacturing, 1800s, that would create patterns, algorithmically based patterns in fabrics. I thought, I'm like, God, yes, absolutely. It checks off all the boxes of what is required for an early computer. It followed an algorithm. And I've never seen in a textbook saying a weaving loom is an early computer. So again, question everything, I guess, is what I'm hopefully communicating here. Okay, let's look at the generations of hardware on computers. So, first generation of computers were built with vacuum tubes. These had a lot of shortcomings. They required a lot of electricity, generate a lot of heat, and heat is computing's enemy, okay? Because of course the vacuum tubes would overheat and fail. At this point in first generation, there really was no programming language except for the machine language itself. And we're going to look at this, okay? We'll look at machine languages, the zeros and ones, and the instruction set, also known as the architecture of a particular computer. But that, I'm getting ahead of myself. We're going to look at that when we get to the chapter on hardware. There were no operating systems. If you wanted to change what a computer did at this juncture, first generation, you had to rewire the computer. If you wanted to change its input, provide it with a different data set, you had to rewire the computer. So first generation of computers, vacuum tubes, essentially no advanced operating system. Of course, you had the machine's programming language, and then and no operating system. Second generation, this was actually a big advance, probably greater if you look at it than any successive generation. The move from vacuum tubes to transistors. We understand Moore's law, where every 18 months, the size of a computer shrinks and it doubles its processing power. Well, this then more than shrunk it by a half, moving from vacuum tubes, we're talking about vacuum tubes that are 3 inches high, to transistors with many processing components in the same space. We did see the evolution of programming languages. The emergence of assembly language occurred during the second generation. And I'll introduce that when we get to programming languages. We saw the evolution to batch processing with our operating systems. And a lot of this was facilitated by the advancement in I/O, punch cards and magnetic tape. Because now with a punch card, I could load a new program. Okay, batch processing. I put a program in, and then with punch cards, I could feed it different data sets. Batch processing. So second generation of computers, hardware-wise, we moved to transistors, but we did see major advances, really, in programming languages to assembly language and operating system to batch processing. Third generation, we moved from transistors to integrated circuits that consisted of many transistors. We did see an advance within programming languages to really the emergence of our first high-level programming languages, COBOL, Fortran. We saw the evolution of operating systems to multi-programming, where now many programs could be in memory at the same time. Only one was executing. We didn't have today's multitasking environment, but we did see a major advance in operating systems as well. We saw the introduction of keyboards, okay, for input, monitors for output, much better than punch cards, okay? And lastly, our present environment, fourth generations, we're looking at microprocessors. And we are seeing now the evolution to a system on a chip, and I'll talk about that too, at least to introduce it here. One of the things that many people don't recognize is as Moore's law, right, things get smaller, cut in half each 18 months, the distances, of course, are shrinking. That's important, okay? Distance matters in computing because the shorter the distance, the quicker the transmission, the faster the computer, okay? So distance does incur latencies. So we're seeing the evolution of more and more things going on a chip. We've seen this in mobile computing. We've seen the Wi-Fi network interface card or Wi-Fi networking functionality move onto the chip. It's closer, it's going to be quicker. So we'll look at this as well when we get to the chapter on hardware. We're seeing great advances in input and output, keyboards, mice, and other things that are here now. Fifth generation, okay? Note that the fifth generation, the textbook says most commonly defined. It's pure speculation at this point, okay? Maybe based on AI. Well, yes, I can directly correlate that if we look at quantum computing, which I'll introduce in further detail in our chapter on hardware. Quantum computing can actually represent more states than just binary on and off, 0 and 1, okay? Quantum computing can actually use and represent more of these states, intermediaries. And why is that important? Recall what computing is, right? It's a study in abstraction. We're dealing with symbolic representation of our real world. What is our real world? I keep looking out the window at our real world. It's analog, right? It's continuous. Whenever we try to represent an analog world, a continuous world, using just 2 states, 0 and 1, okay, discrete, binary, we're going to have error. We're going to have modeling error. We need to take account of this. Quantum computing, of course, improves this because now I have more than just on and off. So it can represent the real world much better. When we look at AI isn't always black and white, right? It's not always yes and no, it could be maybe. And I will introduce fuzzy logic and uncertainty and things like that, kind of going beyond the textbook into AI in this course as well. So yes, fifth generation computers, especially when we speak of the quantum computer, yes, it can more accurately represent, symbolically represent our real world, both the attributes themselves, but also the behaviors. Remember, an object, two things I need to represent: the attributes, its physical attributes, so to speak, and its behaviors. What can it do? The programming. Okay, we're going to look at optical computers. Optical computers have wonderful benefits, especially in security, right? As soon as I have electrons moving, yeah, there's resistance. I need to regenerate them. They're going to generate heat, things like this. Moving photons generates no heat, right? I'm not going to bump up against that maximum of overheating a particular computer. Also, when I look at a moving electron, it generates an electromagnetic field. This actually has security ramifications because this field can be intercepted and interpreted. We don't think about that. You don't actually have to tap a coaxial cable, a physical wire, to actually read what's being transmitted on it or transmitted on it. We can look at the FBI and NSA on that. Whereas an optical computer, right, over fiber optic cable, you cannot just point something at it and know what's being transmitted. So we'll look at this as well. Recall, with every technology, everything we do, we're going to assess it on security, but we're also going to take a look at that IT business society triangle. Okay, contemporary computing. It's also said to be pervasive, also known as ubiquitous. Ubiquitous just means it's everywhere, right? We all have, many of us, I think everybody has a phone at this juncture. And our phones now are computers. They have more processing power than those Apollo spacecraft. So we always have a computer on us, so we can always do computing, ubiquitous or pervasive computing. Great. Convergence. We've also observed and continue to observe convergence. Typical example I can give is the cell phone and the camera. Once those two became integrated, we had a convergence of functionality. And I say that just to reiterate that we need to assess everything from an IT business society perspective. So going back in time, let's look at that. We added a camera to a cell phone, right? That was an IT, an advance in technology. It facilitated a lot of good things. People would take pictures everywhere, right? I look at the plane crash that occurred, the early 2000s in the Hudson River. People took pictures and posted on social media. It was up on social media, I think, 10 to 20 minutes before the first news broadcast. So far more timely. That's a positive societal benefit. Great. But of course, now people had cameras with them all the time. People started taking pictures in places they shouldn't. Children's playground, locker room. And it took some time for society legislation to catch up, right? You cannot take a picture in a locker room of a stranger. We know that, but people were doing it. And of course, the laws had to be written. IT, business, society. Some new technology, and it took some time for business and society to catch up. But it goes the other way as well. Business may introduce some practice that requires some IT development. So again, we assess everything from a security, and then of course that IT business society triangle perspective. Okay, when we look at any discipline, we categorize, right? We distinguish, classify. So when we look at just introducing, computing, we understand that there's hardware and software. And we're going to see, by the way, software, I can further distinguish between system software and application software. As I look at hardware, I can further classify it as internal hardware, inside the box, or external. I'm not going to say anything more on that because we're going to look at that in much more detail in our chapter on hardware. Input, processing, and output. Well, again, this is inherent, required because of our cycle, IPO cycle. Okay, so we need input, processing, and output. Yes. Okay. I'm not going to say much here. Again, we have an entire chapter on input and output and even processing throughout the entire textbook. Again, there are some omissions in the textbook. The textbook does not introduce the Internet of Things and its many sensors. Internet of Things, by the way, you will see by the acronym capital I, lowercase o, capital T, IoT, Internet of Things. And this really is changing the world as well. And I'll go into how it is changing it from a IT business society perspective, but also an economic perspective because of the growth that's taking place. I will introduce one thing, though, at this point with input devices in the IoT. A lot of what the IoT is revealing, we refer to as dark data or dark data, however you want to say data or data. What is dark data? Well, if I put a sensor out there and it starts collecting information, of course, information that was never collected before, it was previously dark, it was unknown. So the IoT and its varied sensors are revealing a lot about our environment, human behavior, all of these things. And of course, they can be fed all this dark data, which will then become big data, can be fed into machine learning, and the machine learning, which is artificial intelligence, can find new relationships and correspondences. And this will be fed into our ability to predict things. And this has both good aspects and bad aspects. And we'll get into that in much more detail throughout this course. Processing devices, well, we're going to introduce and look at, of course, the central processing unit. When we'll look at the graphical processing unit. Now, in the past, many years ago, GPUs were just that. It's just what they did. They did graphics processing so the CPU would not have to. But now GPUs are being used to mine, of course, cryptocurrencies, things like that. So we'll take a look at that application as well. Output devices, again, we have an entire chapter on I/O, so I'm not going to say much, but missing from this introduction and even the entire chapter on output devices are haptics. Haptics are sensory output. The best example I can give is in your car, your lane assist. You start to leave a lane and your steering wheel vibrates. Why? Because that's going to catch your attention much quicker than your speaker going, hey, you're leaving your lane. Or you're backing up and your car detects that maybe you're about to hit something, right? Backup collision avoidance. And your seat vibrates. Because again, that's going to capture your attention much quicker than your speaker going, hey, stop. Storage and communication devices, we have an entire chapter on storage. So we're going to go right down to the base and look at how the zeros and ones, everything is represented. So I'll defer discussion on that. We'll just recognize now, of course, input, processing, output, and storage. And then communications devices. And this has really changed. We don't even think about computing today without its inherent, implied networking. So we'll look at thin client, we'll look at cloud computing, all of these things. But again, our devices are naturally connected. And again, as soon as we connect our devices, we open them up to security and privacy concerns. So we'll look at that as well. So we have hardware, we have software, okay? Software, of course, is, I'll say, virtual at this point. And we're going to look at this. When we look at computing, we have physical resources, your keyboard, your screen, things like that. We also have virtual resources, which are really just zeros and ones in some format that can be interpreted by a particular application. When we start looking at files, your Microsoft Word document, you wrote a paper, okay, great. But it's actually just zeros and ones when it's stored sitting on your hard drive. So we'll look at storage as well. And by the way, it's impossible to speak about storage without the operating system. So I'll introduce that right now. The operating system is your resource manager on the computer. And again, we have an entire chapter on the operating system and what it does. But the operating system governs all actions, all interactions with your computer. when you're typing and writing a paper, okay, and I press the letter J, that's not going to Microsoft Word. It's actually the operating system that's capturing that J and sending it on to Microsoft Word. But again, I'll defer my presentation on that until we get to operating systems. The one thing I will ask you to do at this juncture for the operating system is to read about the boot process. So you can just read this, okay? By the way, the slide, I will go back to CISS100.com just to, again, cover this again. All the PowerPoint slides that I teach from are right here, the top level menu item in lecture modules. So I'll click on it. So I'm covering chapter 1 today. So if you want to get that link, all you need to do is open that up. I'll speak more about the formatting and why I use PDF and why PDFs are required in the Linux lab next week. But you can do the research yourself, research the boot process. Please do this. We need to get a fundamental understanding of how the computer starts up. It's going to become very important. Application software, we have an entire chapter on application software, and it's probably the most thing students are familiar with. We use applications, apps every day on our phones, on our computers. So I'll say no more on that right now. I'm not going to say anything today on computer users and professionals. Much of it is straightforward. What does a computer programmer do? Writes programs, okay? Systems analyst designs systems, okay? But with each chapter, with each successive chapter in this textbook, when we cover networking, you're going to know what a network engineer does and what's required of him. When we cover the chapter on programming, you'll understand what a computer programmer is. So again, I'm going to defer my presentation, and really I probably won't even present this because it'll just become so intuitive as we cover this textbook. Again, when we study any new discipline, we categorize, we classify. So I can classify generic types or categories of computers. Embedded computers, like in our cars, our refrigerators, all of these things. Mobile devices, our phones. Personal computers, our laptops. Okay, so these last three may be new to some people. A server does just that. It provides a resource. An email server, what is it doing? It's providing you with your emails. It's forwarding them to you. Okay. Application server, what does that do? It forwards to you your application. A mainframe computer extends what is commonly just a server. If you think about our Hudson Valley system, we have mainframe computers, right? And for financial aid, for scheduling, for all these tasks that are associated with higher education. But we also have within our mainframe computers our email servers, our application servers that provide the desktop in the computers around campus. Okay. And lastly, on top, the most powerful are the supercomputers. Now note, the distinctions between some of these are very fluid or even subject to interpretation, because today's personal computers actually can serve as servers. In a small business, a really high-end personal computer could even be a mainframe computer. So again, the distinctions are very fluid between these classifications. So embedded computing, again, I'm going to talk about this much more. And really at the very high end, of course, what do we have? Robotics, mobile devices, and again, very, very fluid classification here. Is my computer with a chip for cellular service a personal computer or a mobile device? That's open for interpretation. Portable computers, again, I'm not going to say much. So thin client. I kind of wish the textbook didn't present this right off the bat like this. Thin client computing is a form of client server computing. So really that should have been defined first. What is client server computing? Well, what is the client server model? Well, we can think about a fast food, restaurant, right? You walk in, you're the consumer, you're the client. You place an order, the server presents to you your order, which is of course a resource. So what computer resources do we have? Well, email, right? When you download your email, you have a client machine downloading it from the email server, okay? Application servers, all of these things. But a thin client. So let's go back in history. In the 1960s, if you've ever seen like an old movie, you've seen these rooms with all these terminals. Those were client server. The terminals were dumb, okay? And they needed that mainframe computer to do all their processing. Okay, great. But what did that require? High bandwidth. Now, granted, back in the 1960s, it was just pure text. In today's computing environment, we have multimedia, video streaming, all of these things. So now if it's just strictly client server with the computing we're doing today, our bandwidth requirements would be through the roof, okay? Probably unsustainable because you can't even predict what's coming down the line. And again, we keep increasing the resolution of our videos and all these things, which increases the bandwidth. So it makes sense to do some processing on the client, but still kind of contain this connection to the server, because there are advantages there too. If you look at the computers across campus, the Hudson Valley campus, they're actually part of the ACE, right? The academic computing environment. And what they get, it's a virtual desktop interface, a VDI. So those computers are not loading Microsoft Windows from their hard drives entirely, but they're getting a lot of it also from the mainframe computer. But they're doing a lot of processing locally, so they don't have to continually go back to the mainframe for every answer, which would require a high level of bandwidth from the campus's 3,000 computers that would just completely overwhelm our network. So it makes sense to do some processing locally and some processing on the server. Now, the benefit of the server, of course, if power goes out across Hudson Valley, right, all your computers shut down, you lose your work. But if that work is also backed up or maintained on the server, the Hudson Valley mainframe computers are all running with a generator backup so they don't lose that information. So there are positive advances here. Okay, server's a mid-range computer. Yeah, it can even be a PC. We're going to learn some operating systems are inherently servers. The Linux operating system, Windows is not, okay? Mac actually kind of borders the line there. Mac operating system by itself is actually a kind of a hybrid server operating system. We're going to look at virtualization in depth. And all I'm doing now is introducing it because I really can't speak about virtualization without understanding how the operating system supports it. And what virtualization does actually is it mimics or actually replicates the machine architecture. And it's going to take me a full day to describe the machine architecture and its instruction set. So virtualization allows you to create virtual environments. And I'll leave it at that. Mainframe computer, more powerful computer, yes. So really we look at a mainframe as being maintained by an organization. Typically a mainframe, if an organization requires a mainframe computer, it will have somewhat of a data center. Because again, computing, these hardware components create a lot of heat. So it makes sense to put it in its own room, air condition it, provide with the additional environmentals, back it up, provide generator support should power go out, etc. And at the very high end, of course, supercomputers. I'm not going to say much about that at this juncture. Computer networks, the internet, the World Wide Web. At this juncture, let's just recognize the internet and the World Wide Web are not the same thing. The World Wide Web runs on the internet. The internet is a widely connected, heterogeneous network. So I did just introduce that term, heterogeneous, which means diverse, many things, versus homogeneous, singular. So again, I will come back because I will use those terms throughout this course. So understand that distinction. So of course, today in our computing, we don't even think about computing without network connectivity and support. You know, we take it for granted. That wasn't always the case. Pardon me. What is the World Wide Web? The World Wide Web is just a service, okay, linked information that is accessible through the internet. And there's a lot of things taking place on the internet. Phone calls, VoIP, voice over IP, okay, are taking place on the internet. We have converged communications. So converged word again. So the World Wide Web, okay, is just one resource that exists or is accessible on the internet. Web pages, of course, are accessed through hyperlinks or URLs, Uniform Resource Locators. We have an entire chapter, actually 2 chapters, on networking in the internet. So I'm not going to get into the specifics of network adapters. What we're talking about is network interface cards, modems, routers, the messages, their encodings, the mediums is a copper cable, wireless, fiber optic. All of these things I will cover in detail when we get to those chapters. Now, likely I will go beyond the textbook there as well. When we look at internet addresses are essentially numeric, but we don't access them through IP addresses, right? We as humans don't deal with numbers as well as characters and words, right? I likely would not memorize the IP address of all the sites I visit. Whereas with URLs and domain names, ESPN.com, CNN.com, I can get to whatever site I want to, okay? Because it's the way that we think of the world. I probably would not memorize, I wouldn't want to actually, there's other issues here, that CNN's IP address is 64.26. whatever, okay? It really would not be the way that we work. We do need to recognize that we have recently evolved from IPv4 to IPv6, okay? I'm not going to say much more on that. I'm going to get to addressing when we get to hardware. So again, Uniform Resource Locators, URLs, is really the way that we see the web. It makes it much more accessible or usable. A lot of this too, again, is very straightforward in the text, so I'm not going to say anything on email addresses. But we do need to understand and distinguish, of course, between usernames, j.luby, and domain names, hvcc.edu, and of course, they're linked with that @ symbol. And this will become very important in the Linux labs. Again, this is that exacting attention to detail that we have to develop. And again, nobody has taught us how to do this. We all go through this. I went through this. Every computer scientist goes through this learning curve, this detailed, precise learning curve. This is about the last thing I'm going to say on this chapter. The rest is pretty much straightforward. Cloud computing. What is cloud computing? Well, it's client-server computing, which the text really did not define at this point. I give a very superficial definition of it. Cloud computing makes client-server computing accessible. Why? Because it's accessed through a web interface. When I say web interface, it's formatted with HTML, or through HTML, Hypertext Markup Language, HTML. Because if some resource is presented to me through HTML, any browser can render it, right? It becomes accessible from every device. I'm going to go into cloud computing in much more detail when we get to systems analysis, the internet, and other things. But really, there's no mystery to cloud computing. It's client-server computing with a web interface. That's it. I'm not going to say a word on surfing the web. I'm sure everybody does it. I'm not going to say much on searching the web, except that increasingly, we need to be able to evaluate, right, the veracity, the truthfulness of what we find. And there's a lot going on. I'm going to say more on that. Email, everybody's using it. I'm not going to say anything. Again, the remainder of the chapter just goes into technology and really recognizes without saying the interrelated nature of the IT business society triangle. If anything changes in any one of these triangles' vertices, it's going to drive effects in the other two. So there are a lot of benefits, a lot of risks, security, privacy, we know the benefits. That's essentially the chapter. I'll let everyone read being nice in online communications, things like that. If you have any questions, let me know. Otherwise, by Sunday night, 9 p.m., lecture module 1 is due, which includes the intro and syllabus quiz, quiz 1 on chapter 1, and discussion board 1. There's Linux Lab 1, which is just reading, but please make sure you do it. Okay, the reading is critical to everyone's success. That's all I have. Have a great week. If I can help anyone in any way, just let me know. Thanks.
Have a good day.
Thank you very much. You as well.
Have a good day.
Thank you very much.